Historically, the automotive industry defined safety through the lens of hardware and software reliability. If you could prevent a sensor from short-circuiting or a line of code from crashing, the vehicle met the standard for safety. The SOTF standard, Safety of the Intended Functionality, addresses a different kind of failure. It accounts for AI systems that function with zero mechanical defects, yet still cause disasters by misinterpreting the physical world. Engineers map this challenge using a 2x2 matrix. The known safe area represents environments we understand, while the unknown unsafe quadrant contains rare, dangerous variables the system has yet to encounter. Modern engineering focuses on shrinking that dark quadrant, converting blind spots into known, safe data. In this framework, safety depends on how accurately the vehicle understands and responds to the complexity of its surroundings. The physical world contains an infinite number of variables, factors like road curvature, sudden changes in precipitation, and the angle of the sun. In most cases, these elements are harmless. Danger emerges when these variables align into a triggering condition, a specific set of circumstances that exploits an AI sensor's inherent blind spot. Imagine a white commercial truck driving on a highway just as the sun sets directly ahead of it, creating an intense direct backlight. Even with a perfectly functioning camera, the sensor's dynamic range is exceeded. The white truck bleeds into the bright sky, disappearing from the machine's vision. Because the AI perceives only an empty horizon, it never triggers the emergency brakes. This single failure point demonstrates why testing vehicles in standard, predictable environments cannot guarantee they are ready for real-world survival. Engineers cannot physically drive enough miles to encounter every possible permutation of weather and traffic in the real world. To solve this, the industry uses the Pegasus 6-layer model to translate physical environments into a structured digital architecture. The foundational layer maps the physical road geometry, the curves, hills, and exact lane counts of a specific route. The next layer adds static infrastructure, showing where traffic lights, signs, and barriers are permanently placed. Then come the dynamic elements. Engineers inject moving cars, bicycles, and pedestrians, each with their own speed and trajectory. Finally, the environmental layer introduces variables like dense fog, rain, or heavy sun glare. This stacked approach allows engineers to isolate and manipulate every single variable of a driving environment within a virtual simulator. Dissecting reality into layers converts unpredictable environmental data into a structured grid for stress testing. Even with this digital grid, testing every possible combination of all 6 layers would require thousands of computing time. To navigate this, engineers use combinatorial pairwise testing to identify the most likely failure points. This method is based on a key finding in software engineering. Most failures are triggered by the interaction of just 2 specific variables, rather than a complex pileup of dozens of factors. Here, a variable from the environment layer, like dense fog, collides with a dynamic layer variable, like a black vehicle. By testing every pair at least once, the process bypasses millions of safe, redundant combinations, isolating the interactions most likely to cause a sensor to fail. This focuses testing resources on high-risk interactions, finding the specific blind spots that matter, without wasting time on territory already proven to be safe. Engineers take these high-risk pairs and intentionally force the AI to face them in punishing virtual simulations. By identifying where the system breaks virtually, engineers can update the code to handle those specific conditions before the vehicle ever touches real pavement. Total safety relies on an ongoing effort to map the unknown, ensuring the vehicle stays prepared for rare and evolving hazards.